All right, next up is Spiros guys who's going to be talking about OCI containers.
Thank you. Hello, I'm Spiros. I'm computing engineer at the Cell Cloud team, and I'm the project team on the OpenStack management project. It's the container infrastructure management project of OpenStack. And I'm going to talk about OCI containers. So, OCI containers. First, let me say that the Linux containers are just processes, normal processes controlled by Linux kernel, by Linux control groups, and namespaces. So it's totally different LVM. So it's a totally new mindset. But specifically about OCI containers, the most popular containers are containers managed by Docker, and in 2015, Docker and other vendors created the OCI specification. So the OCI specification has three parts. It's the runtime specification that defines how the runtime should understand the configuration which describes the container and how it should run it, how it should create mounts, namespaces, and use capabilities, and how to do the lifecycle operations of the container. Then there is the image spec, which defines how the image should be composed, that the image should have a manifest that describes the layers with the image index, and also the set of layers described in the image index. And of course it has the configuration configuration. And finally, it's the file system bundle. So when the container runtime or any other tool pulls an image that is OCI compliant, it extracts it in a file system bundle that has a root file system where the container will start, and the configuration which points to that root file system and describes all the capabilities and what is the dimension. But why we need the OCI containers? So, as I said, containers are just Linux processes. So, you need someone to start the container. And most likely, if you have more than one containers, you need a supervisor of these containers. If you are in a large deployment, most probably you orchestrate the containers. So, you have a system like Docker Swarm, or Kubernetes, or Nomad, or Mesos, DCS, something else. But if you are in a single host and you don't want to orchestrate, you need something to manage your containers. In most Linux distributions, processes are managed by systemd. So an idea would be to manage Docker containers with systemd, but that means you give the code to systemd, and then systemd does a code to Docker daemon, and then Docker daemon talks to the kernel to create a container. This has some indirections because when you talk to the Docker daemon, the Docker client, you do an API call. So that might be asynchronous, and you introduce an indirection in systemd. So it's better to manage containers either directly with a Docker daemon or with systemd. Another use case is Kubernetes. Kubernetes was initially started by having by talking to Docker, but that means again that meant again that it was doing API calls to the Docker daemon. So in Kubernetes, where with a component that creates the actual containers, which is kubelet, they created the CRI specification. And there are a couple of CRI specification implementations. Like one is the CRI container D and the CRI-O. Container D is a project of the daemon that is behind Docker now, and it's developed by Docker team and other contributors. And CRI-O is another specification that is another implementation of the CRI specification that is implemented initially by Red Hat and other contributors, and it was based in the previous design of Docker. So the use case for all of that is, and one more use case that I will describe later is like a chicken egg problem. So what if you need a process that needs to start before Docker and potentially manage Docker or configure Docker. So if you have an orchestrated environment based on Docker, you might not be able to run all your containers as Docker containers, so you might want both of them. So in this talk, I will try to motivate why I got into this. So I would like to clarify that I'm coming from the user's perspective. I'm not the developer of the OCI specification or any of these tools, but I'm actually the user and consumer of them. So all this consumption comes from the CERN container service. So at CERN, we have just 1 minute to describe what CERN is. I hope that you already know. It's the European Council of Nuclear Research, and that does fundamental analysis and most probably particle physics. So at CERN we have a big accelerator that accelerates the protons that create collisions, and these collisions create events and lots of data. So our biggest use case is batch processing to process all this data. And in 2018 or since 2015, containers are a very good use case to define workloads that will run in a computing grid or in a clustered environments. So there is the biggest motivation. Other use cases are end user analysis, which are most prominently defined by Jupyter notebooks, that you can build a container that essentially it's a notebook, and you can do analysis and then share the container images so that other places elsewhere can do the same analysis and be sure that it will run in the same environment and it will have exactly the same results. Other cases that all IT companies and IT environments have is transaction management, continuous integration and deployment. As we are a big OpenStack shop, we also run OpenStack in containers and other use cases. So the container service is based on a project called Magnum, since I'm the project lead in Michigan. So this is a very simple workflow of it. So in the first command, you just create a cluster, and you say, in this case, that I want a Docker Swarm cluster with 100 nodes, and you wait some time, in our cases, 5 minutes or maybe less or more, depending on the environment. You wait for the cluster to be complete, and then you just get the credentials to talk directly to the Docker daemon on the master nodes, and just orchestrate your containers. And in this case, as you can see, after 2 commands, you don't have to do list. You start to talk to the cluster and the Docker daemon, so no OpenStack anymore. And this is how a node looks, even if it's Swarm or Kubernetes in this environment that Magnum creates. So in the upper box, we have a Swarm cluster that has a Docker daemon. In the legacy Swarm, before Swarm mode, you have a Swarm agent that's running a container on every node. You also have the etcd that should run only, or console that should run only in master nodes. In our case, we have some SERM plugins which we run them in containers, and then we have an OpenStack agent that takes configuration from OpenStack and applies it to the nodes. Similarly, and even more complicated in the Kubernetes use case, we have more Kubernetes components. We have Flannel, we have etcd, we have a CRI runtime, and then we have the agent and the plugins that we want. So in the case of, for example, for the legacy Swarm, if you wanted to run etcd in a container, you should, and you had only Docker, it's a chicken egg problem, because you need to start etcd before starting Docker. So if you want to start this Docker container, there is a deadlock there. So what we want to do is to start in etcd in a different way, like as a managed container by systemd, and then deploy the Swarm cluster. It's exactly a similar use case in Kubernetes. So if you want to run, for example, kubelet in a container, and if you want to run kubelet in a container managed by Docker and kubelet, you need to, you cannot know which one to start first. So in our case, we can start kubelet in a system managed container, and then we can start Docker again in a system container, and then stop that container and start the pod in that node. And of course, the other use case is the OpenStack agent, which defines and configures all of this. So since this agent configures everything, it must start first before all. So this was the initial motivation. And for these problems, we end up looking in OCI containers. So how to build them? I was about to describe a build-up, but since I found it more complicated, I think it's easier to build manually. So a system container is a container that runs in atomic hosts. And the project Atomic has Fedora and CentOS atomic hosts. And if you are in the enterprise world, they have a Red Hat offers the Red atomic host. But in our case, we use Fedora or CentOS. This comes with the atomic utility and some set of other tools that allows you to create containers to be managed by systemd. To build those containers, that you must build them and to be OCI compliant. So we have a Docker file, and then we use Docker to build the image, and then we have a systemd template which will be added to the Docker image, and then extracted by the atomic utility and deployed on the node. So then systemd knows how to manage that container with run C. We have a list of TMP files, which are files that may be that container to do some bind mounts, assumes that they exist on the host, but maybe they don't. And then manifestation, which are default values for the application that runs in the container, and the configuration, which is the standard from the OCI specification. You can have a look on all these files in the link that I put below. So this is how it looks to build the container. There is a hello world example, of course, in the atomic system containers repo. So you just build the hello world atomic, the hello world container as a normal one that you would do with Docker, and then you push it to a registry. Then you can just do atomic install, which is only an atomic host, but there's also available in Debian-based systems. And you do atomic install minus system, which means that it will run as root, unless you specify otherwise in the configuration. And then you can give it a name, and that name will create a systemd service based on that template. And then you can do just systemctl start forward, and it start that systemd service. So in our case, it was a better solution. We could program whatever clients and OpenStack specific tools that we wanted, and without modifying the host. So treating the host as a mutable infrastructure, that we don't take host and we install a bunch of things, or we don't just rebuild hosts all the time. We just take the actual distribution and then we extend it as we want. But if you start looking into OCI containers, and if you ask anyone that works on them, the most difficult part is to create the configuration file. And so in one of the first websites and documentation of RunC in the OCI specification, they said this is how to create a template, and then you populate it. That period, there was nothing. After that, there was no documentation. So you should start starting about the namespaces. I put the URL on the man page of the kernel, but the bare minimum that you need as an advice is the mount namespace, because if you run a process without a mount namespace, it just starts in the file system of the host. So the root file system of the container just goes away and you don't use it. Probably you should add IPC, but it's not important. Then you should add a user to have a user namespaces and separate processes by user. And then you might also need the ID to have, if you have more than one processes in your container, you might want to have a different namespace. And usually for system containers, which are containers that are very close to the host, you usually don't want to add a network namespace. It's better not to add it and share the same network namespace with the host. Then it's the capabilities. If you go to the website that I list here of the Linux kernel man pages, the number of capabilities is endless. So one advice that I have that it's a very cool hack is if you start a container with Docker and you want to find, okay, this container that runs in Docker, what capabilities it's using, this is a very cool hack how to find it. You get the PID of Docker, and then you go to the prop file system, and with some grep and doc, you can find exactly which capabilities you need. So this is one of the first iterations that I was doing for my containers. And then, of course, you have mounts. So in mounts, you should be able to understand when do you want, or what do you want to share with your host or share with your other containers. So in this case, this mount is a bind mount. The container will have read-write access, and these are private. So that means only my container will have access to that directory, and changes that I'm doing there are not propagated to the host. If they're going to be propagated, as you have used, are shared. And there is also the possibility to have slave, which means only the host can change, and then they are propagated to the container. I think that concludes my talk. I finished a few minutes early, so I put in some links here, and that I advise you, if you are into containers, to go have a look at the runtime and the image spec. They are not very long, and they are very, very well defined. Don't follow all the links that they have, because they go to RX specifications which are extremely long. And you can check the OpenStack system containers repo that I contributed and the atomic team contributes, and you can base your own containers there. Of course, I teach my project, which is the Atom project there in OpenStack. And if you have any questions, you can bring me on Freenode and Twitter. Thank you.
Questions?
Let's say, for example, that I am an Emacs user and I have a lot of plugins and a lot of settings. Can I make a container with my Emacs, my plugins, my settings? Then whichever machine I'm running, I tell, for example, Docker to run this container, it's going to run with the user of that machine, and not the super user or some specific user in the container.
Yes, you can do, if it's defined in the documentation, Docker will follow the specification, because Docker is an OCI compliant runtime, so it will do it. And these containers that I described, apart from some special files to the system units, are just normal containers that Docker runs them as any other containers.
Yeah, but how does Docker know which user was the user that spawned the container?
Usually the containers that spawn them as root, but then they run as a different user. They're not rootless containers.
Yeah, but how does he know who called them? The user who invoked the container must know that, so that he can become this user.
The user that created the container in the first place will be root, and then inside the container, the user will be specified with the user ID and the 2 byte.